Well, it's actually my pleasure to introduce today to Professor Kitanovski. He's the head of the refrigeration and actually district energy team at the University of Ljubljana. He's actually the head of this department, and you have under your umbrella around 20 people that are working on different topics, from fundamental actually to applied research. And this is one of the special things of Professor Kitanovski, that is actually capable to connect some fundamental aspects of science with something really applied. I met Andrej many years ago already in a conference in Leuven, and we have been interacting since then due to our common interest of actually bringing together fundamental concepts of science towards something more applied. So, Andrej, the floor is yours. Looking forward to listening to your presentation.
Okay, thank you very much, Mikel. Hi. As Mikel already presented me, our group actually consists of mechanical engineers and physicists. So half of these people are physicists or material scientists, actually. And we are also in other domains, let's say, of energy conversion related to conventional technologies like solar, thermal, solar photovoltaic, thermal storage systems, and so on.
Andrej,
yeah.
yes, one second. I forgot to mention that this, stay of Andrej here is actually a privilege, and that has been actually possible thanks to the planned visita of the Institute of Material Science. My apologies, Andrej.
Yeah, and this is why I would also like to thank for the invitation and to have the pleasure to be here and to see the work and communicate with other researchers. Okay, so just shortly about Slovenia. It's a very small country. We have only 2 million people. The surface is quite large. We have the third largest European forestation, so after Finland and Sweden, so a lot of forests. The GDP is not so bad. We have the best economy of the ex-communist countries who joined the European Union. This is the capital of Slovenia. It's Ljubljana. In the Roman times, it was called Emona. It is 2,000 years old town. Before Romans, there were actually Celtic people living in this region. The largest university which we have is actually the University of Ljubljana. That's the headquarters, it dates back about 300 years ago. They started with theology and such stuff, and then they continued a bit with also other things, but especially at the beginning of the 19th century. So the Faculty of Mechanical Engineering lies actually still in the center of town. This is the old building. All these buildings here, you see, everything here is actually the Faculty of Mechanical Engineering. And we are moving out now as most of the technical universities, let's say, or faculties, we are moving to the vicinity of the technology park. So this is the new building. We just got the permission to build it, and it will be built probably in 4 years. Also, we are really happy because you know that in all buildings it's very difficult to find place for the equipment. So we sometimes need to demolish prototypes just to have more space. Now, I would like to start actually with the motivation of my talk. And I will just briefly go why we do what we do in the lab, and why caloric energy conversion and storage is the title of this talk is dedicated to. So here you can see some global figures about the heating. We all speak about the decarbonization, green transition and so on, sustainability. But when you see the policy actually also in the European Union, it is rarely addressed that 50% of the total energy consumption is only cooling and heating. It is not transport, it is actually cooling and heating. And much of these sources actually causes actually the major CO2 emissions in the world. What is more is actually that we waste a lot of heat. So we waste most of the heat from different sectors, and related, let's say, to the global energy consumption, this waste heat presents actually 50% of the final global energy consumption. So it's also 50% of the heating and cooling we need for the from the final energy use, and actually 50% of the final energy use ends as the waste heat, which is wasted. So this is really funny to see these high numbers, because they are much higher than in any transport domain. And there is, of course, also large room for improvements. When we focus on cooling, that's a bit different. That goes about 20% of final electricity consumption. Global electricity consumption is actually related to air conditioning and cooling. And refrigerants, today's refrigerants cause 8% of global warming emissions. I'm speaking about the refrigerants which are related to most of our devices which we use, and these are actually vapor compression devices. Okay, which is interesting to see is actually how International Energy Agency sees the development in the future about air conditioning and cooling. They say that it will triple until 2050, which is an enormous number. Now somebody could say, okay, that's because of the global warming. No, it's not so much. If you see, we have well-insulated houses, nice houses, glassy buildings, and we have a lot of internal heat sources from our computers. And then also we have higher comfort of living as it was in the past. So this is actually everything together is causing actually the increase of the needs for air conditioning and cooling. And then also because of all the world is developing further on, these needs need to be covered. Now the refrigerants, when we start, let's say from the beginning, the first refrigerants which were used in vapor compression were natural refrigerants. And then they did jump to chlorofluorocarbons, which caused ozone layer depression. And then we had actually also others like hydrofluorocarbons and so on, which caused actually the global warming. And slowly we are trying to get rid of them. Coming back to natural refrigerant. So in general, actually, all the future of the vapor compression and air conditioning will be related actually to natural refrigerants or hydrocarbons. So the problem of these refrigerants is actually flammability. We have explosion hazard in some cases, toxicity, high pressures. And that's actually related to all the natural refrigerants, or most of them, and hydrocarbons as well. But actually this problem can be solved. What you will see, there is another type of the refrigerants which was mostly developed in United States, and it is related to US companies. It is actually, it does have strong environmental impacts. But I would say those who work with these refrigerants will not really admit that this is true. I speak about hydrofluoroolefins, which cause acidic rain, and that was very well investigated by Danish and German researchers. So this was actually proved, and this is very problematic. But most of the people who are seeing, let's say, the future of vapor compression say, yeah, these hydrofluoroolefins could actually replace the problematic hydrocarbons, or let's say natural refrigerants, because of their weaknesses. Okay, I think before going into some development of some kind of technology, we need to know what the existing technologies are. So we need to know what we are doing actually, because just to do something and not to study what's going on the market, or let's say what exists, doesn't make sense. Because we cannot claim, for instance, that photovoltaic cell of 10% would be better than the one on the market if we do not know what is on the market. And so this is actually a process of learning. And this what you can see here is actually just a bit the three diagrams of air conditioning and cooling. In the first diagram on the left side, you can see it is shown actually a kind of Carnot efficiency of cooling-related devices, starting from cryogenics up to room and then temperature and above. So it's obviously in this blue region, which you see here, it's actually market available devices. So if we develop something which is below, would not really make sense from the point of view of our statement that we want to have a better efficiency. So we need to overcome this if we want to beat, let's say, or we want to improve the sustainability of any kind of technology. And it is not only this, but then when we want to sell it, the very important part is actually the cost. And the cost is always related to the power density of device. So you need to have a small device which weighs nothing, costs minimum, and performs excellent. So, of course, that's a dream. And this is actually the real data of vapor compression systems related to the cooling power. So you can see smaller devices have actually a bit bigger mass related to the power than big devices, huge devices, which you see here. It's really huge number. It's megawatts. And also the refrigerant part is actually increasing. So how many kilowatts per kilo of refrigerants can you get out from a device? Why I'm showing this? Because this is related to the development of caloric technologies. I'm involved in caloric since 2003. And we were really pioneering some of first prototypes in the world, not only in magnetocalorics, but also in electrocalorics, using magnetocaloric or ferroelectric, let's say, also materials. This is how I would like to show why do we do that then. So the caloric energy conversion and storage, we see it, let's say, as the potential for cooling, as the alternative to vapor compression, so alternative to refrigerants, but I will show also other potential advantages, theoretical ones. Then it's nice for heat pumping, energy harvesting, but also solid state phase change thermal storage. And these four domains are of the interest of researchers who do actually research in caloric technologies. Now, before going to calorics, I would like just to address why we do that. So first one is actually the second law efficiency of devices based on, let's say, caloric effects can beat vapor compression. Because the vapor compression takes over, let's say, 95% of the market, and it is the best possible technology for refrigeration and air conditioning and heat pumping. So energy efficiency first is also the European directive, so we are really targeting something that could go beyond. And theoretically it could, because we see that the effects can be really reversible when you compare, let's say, a vapor compression is a polytropic process thermodynamically, and of course it's not isentropic, and the changes, let's say, of the magnetization, demagnetization of, for instance, gadolinium magnetocaloric material are reversible. So the entropy change will be zero when you magnetize and demagnetize, so almost zero. So, and that means actually that we can really gain a lot by the efficiency. But there are, of course, other problems which are associated with this, and I will come this to later. So possibility of having no moving parts is very important. Vapor compression uses moving parts. We have compressors which are based on pistons, turbines, and so on. Spirals, and especially when related to, let's say, so-called magnetocaloric and electrocaloric technologies, we can really provide a device or develop it which does not contain any moving part. Similar as thermoelectrics. So this is also one thing which is very important for us. Possibility to recycle solid refrigerants, which cannot be really done for vapor compression. Scaling down, let's say, of vapor compression is not possible for, let's say, microwatts, watts, milliwatts, or up to the range of 10 watts, for instance, of cooling. And we see today, for instance, your household refrigerator will in future need probably 10 watts or 15 watts of cooling. because they will implement vacuum insulation inside, improve it so much that probably you will need really a very small power to run it. And vapor compression is not ready for this, because when you go to small powers, the efficiency substantially drops. Okay, new and different or special applications, which are not possible with fluidic-based, let's say, devices. Vapor compression is also limited to the temperature range between minus 100 degrees centigrade to up to, let's say, 250. Above this, it will not work. Below this as well, not. Heat to power energy harvesting below 80 degrees is not possible with most of devices. The only technology which today really allows conversion of heat, let's say, into the useful work is thermoelectrics. And caloric technologies are actually a kind of, I would say, temperature differential devices like Stirling. So in any kind of temperature differential, they would actually operate. It's not important at which, let's say, temperature level. About the storage, I will come back later to this, but we can store heat in, let's say, phase change solid state materials, but on the other hand, all the caloric materials are phase change solid state. So this is also the interest which we are looking for, because we have phase change there. You can really see when you observe the specific heat, and then we are dealing also with the first and second order transition, of course, but there are plenty of materials. Now, if I just jump now on the four main effects, I would just slowly go. Let's say we deal actually with a kind of I-caloric or I-pyro. I-pyro would be related to power generation, and this one for cooling and heating. And that means that actually we can, let's say, use magnetocaloric materials where we change order. By applying the magnetic field, or we change actually order in ferroelectrics by applying electric field. And an analogy from the point of view of thermodynamics is super cool. Really, it's very easy to understand. When you understand one cycle, let's say one type of the principle, you can understand all of them. Of course, then if you enter from the other point of view and you study materials, this is totally different. So people from electrocalorics do not collaborate with people from magnetocalorics. They're both solid state physicists, material scientists, but they do not know for each other. So we brought them together. But you know, one is playing with electroceramics, the other guy is playing with polymers, which is soft matter. And then the third one is interested only in magnetism. So it's really plenty of different, let's say, how would I say, societies, which you need to merge. But in general, looking from the thermodynamic point of view, I do not see any difference in device. That's very interesting. Okay, so it's not only this. Then we have elastocalorics, where you, for instance, very well known is nitinol, for instance, a material for nickel titanium. You know, you call it usually nitinol, it started with this, let's say, for elastocalorics, and then we have also recently, let's say, many papers, new papers coming out on barocalorics. So different kinds of effects can actually lead to heating of the material when applied to the field, and then cooling down when the field is released. So by this, actually, we can really build different kinds of principles of devices, whether applying actually a magnetic field, electric field, stress, or that we can combine even those. So there are possibilities that actually you make a composite of two materials, or you have actually a multicaloric effect where you gain two effects. For instance, you apply electric field and stress, and you get actually a kind of, I could say, let's say, a kind of elastocaloric effect together with the electrocaloric effect to multiply the change. And this change corresponds to usually to adiabatic temperature change, we say. So the temperature jumps, the entropy, the material entropy goes down usually, and the total entropy increases. Or let's say the total entropy stays the same, more or less, unless you have, let's say, hysteretic material. And this is why material heats up. And when you release actually the field, it will cool down. Of course, we know also antiferromagnetic and antiferroelectric materials, which will cool down when applying the field. So we have a lot of different possibilities here. And now the device which you can build needs also heat transfer, because it's not only the applying the field, but you need actually to shift and to bring the thermodynamic cycle, which means that you need to bring heat from the heat source, and you need to reject heat to the heat sink. This is a normal operation of a device. I will come back to this issue later. And just to speak about solid state thermal storage, these are a bit advantages which we see, for instance, in solid state change than compared to, let's say, paraffins and hydrate salts, which are commonly used in phase change material storage. So the latent heat here is bigger, but the density is smaller. They operate in a narrow temperature interval. Okay, that could be also related to calorics. But if you have hysteresis, usually you have a bit bigger temperature span. But which is more important is you cannot attach paraffin directly to the fluid, the working fluid. You need a kind of intermediate heat transfer surface, which actually requires actually a volume, and you reduce, you increase the irreversible heat transfer because of this, and then the device is not so fastly operating as the one which could be based on, let's say, caloric materials. So this is one of the studies which we do. These are a bit materials. That's an overview of different kinds of materials, and here you can see also some of the calorics inside. MCM is magnetocaloric, barocaloric, elastocaloric, and you can see a few of them. Okay, so the basic principle of operation, I will explain it, let's say, through the active magnetic regeneration. This is the most basic process which is used actually for cooling. And I mean, the process will be very similar in electrocalorics or barocalorics and I would say the elastocaloric. So let's say now that this cycle, you will see a bit regenerator. That's very primitive, but just you see two pistons. These two pistons will move actually now the fluid, and inside this structure you see a kind of magnet, let's say magnetic flux lines, and you have two heat exchangers here. This is a heat source, this is heat sink. And of course, this magnet will actually cause the ordered state of in the material, which means that it will heat it up. And here you can see a kind of material in a form of plates. This is, let's say, plates of magnetocaloric material. And of course, by doing this and shifting the field, we are changing the temperature of the material. And when we do that, now you will see also later on different forms of this material. So in general, when what you will see now later on is actually that when we apply field, we will need to push the fluid from heat source to the heat sink, just to evacuate this heat which was generated away to the heat sink. Now, and then we will move away the magnet, or let's say the field source. The material will cool down, and we will push it in opposite direction. That means that we will have a kind of oscillation of the fluid flow inside. This is how, in a steady state condition, after a while you can reach actually a temperature gradient between the heat source and heat sink, which means actually you can cool down or you can heat up. Yeah, sorry, just go back. I find it, it will go fast now. Okay, so just again to repeat, the point is actually that you always need to oscillate the fluid, but corresponding, it should correspond actually to the movement of, or let's say the change of the magnetic field, or electric field, or stress. So this is the basic principle, and of course you see moving parts here, because most of the devices which were built in calorics are built on moving parts, based on the moving parts. So in related to regenerators, for instance, in magnetocalorics, you can use packed beds of spheres, parallel plates, honeycomb structures. So there may be ordered structures, or let's say disordered, like packed beds. You can see now that the changes of the colors show what happens actually when the magnet goes up, the material will heat up, but you can all the time see some kind of gradient. In a steady state, of course, you would see actually the gradient between the heat source and heat sink. Now, these are a bit magnetocaloric materials. We cannot do the same with, let's say, elastocaloric. So in elastocalorics, usually you will have a kind of wires, or let's say a kind of honeycomb structure. In electrocalorics, usually people will use plates. They can make also a kind of structure like this, but it's quite difficult. It depends what kind of material you use. Usually nowadays we use, let's say, a kind of in ceramics multi-layers. Then there are thin films, but thin films are really thin. If I speak about polymers, you need to make a bit bigger structure if you want to get anything out of it. Otherwise, we speak about milliwatts of power. So this is actually a challenge. So where are we today? I will just go shortly through the history, not really history, last 20 years of developments in magnetocalorics. An example why I show magnetocalorics is because it is the oldest from the caloric technologies and the most developed. It started, I think, in 1997 with the first prototype, which for the room temperature application. You know that magnetocalorics, for that people won a Nobel Prize, actually, because it was recognized as one of the new technologies for cryogenic cooling to approach actually the 0 Kelvin. But then nobody touched this topic really until, let's say, 1980s, 1990s, and you can see here then the evolution a bit. I will not show everything, but the last 20 years, you can really see the real prototype devices, based on rotation of magnetic fields, linear movements over the magnetocaloric material. You can really see what I'm showing here is actually mechanical engineering now. Yeah. But for this, you need actually a heart of the machine, which is actually magnetocaloric material. And this is why the collaboration started, which was very interdisciplinary between different domains, which is very interesting. I will show you later, Yeah, that was one of the prototypes which was based on permanent magnets. Most of this is only permanent magnets here, which you see here. But then also, in the later stages, these were really huge devices. Then we got some companies, startups. That's a 10 kilowatt machine. They call it air conditioner. I mean, this is really heavy, but still, people are trying to do that. We were involved in development of this one in collaboration with DTU. And that was actually a household heat pump. So we were really trying to do many different kinds of devices. And most of them, let's say in general, they were actually rotating. That means rotating magnetic field or rotating magnetocaloric material in a static magnetic field provided by the permanent magnet assembly. So we learned a lot about how to design magnets. I can design today very nice permanent magnets. So I learned to do that because I was forced to do that. This is how I learned also about magnetism. And by having colleagues from material science, I learned a lot about the materials because we were sitting in the same room and speaking to each other and listening to each other. So that was really nice. One of the last prototypes which we built was actually for Gureni Hisense company. That was a wine cooler. For this particular case, actually, we used electromagnet because we developed a new type of the magnet which has actually a very rapid change of the magnetic field. We could run it with 50 Hertz, a step function of 1 Tesla in let's say 10 milliseconds. We have new ones now going up to 1.5 Tesla in the same time, but with higher frequency even. Okay, but speaking about cryogenics, then we come to superconducting magnets. Of course, higher the field is applied, larger the temperature span will be given by the material, and this is actually very important because higher the field is and larger the adiabatic temperature change means actually that you can get actually better efficiency also, because you compensate the big irreversible heat losses by having larger temperature spans when you are magnetized, polarized, or whatever with this material. So you can see a lot of progress has been done actually in using superconducting magnets actually for cryogenics, especially liquefaction of any kind of fuels, let's say fuels or gases. That was actually also, so you can see propane, hydrogen here, oxygen, then we have actually here, okay, hydrogen again, methane, biomethane. So it's really a lot of ideas how to use it. But of course, people they just use a normal cryo cooler, you know, and they put some pill inside and move it in and out, and they try to do something with caloric materials, which are really magnetocaloric materials at very low temperatures are really good. We found out actually that for other types of caloric materials, NASA did some studies in 90s, probably 80s, about electrocaloric materials. And then nothing happened. So a lot of people want to restart this because compared to, let's say, magnetocalorics, electrocalorics can really provide perhaps more simple devices, lighter, and this can be very important. So, okay, not to mention also ferrofluids. Ferrofluids are nanofluids. You have nanoparticles suspended actually in a carrier fluid. The pioneer in this field is actually Rosenzweig, Ronald. He's actually the inventor of ferrofluid. He opened the company. And I had the privilege to, and I have the privilege to know him. He's very old now. And he taught me about magnetocalorics. Because he did in 1960s and 1970s, in 1960s actually, he wrote some papers about how to make the magnetocaloric energy conversion by using magnetocaloric fluids. They were dreaming about how to use waste heat and convert it into electricity by having, let's say, no moving parts or moving parts and so on. Today, actually, we tried this as well. So when you apply the heat source and heat sink over a static magnetic field, you can get actually the pressure difference, which makes the propulsion of the fluid. This means that you do not have a pump, but you need a heat actually and magnets to propel the fluid, which can run over, let's say, the heat sink or heat source, without any moving parts or external, let's say, power. But there were some ideas actually how to use this also in some other domains. Okay, in the recent years, this was actually the revisited domain, thermomagnetics, how to make the power generation. But thermomagnetics starts in 1700. about. The first idea, the Curie wheel, and then was later, but how to make thermomagnetic power generation. There was just an idea how to change the magnetization due to the temperature difference, and that change would cause actually the change in the force, and the change in the force would make a linear movement or the rotation. So there are some ideas, and these ideas came to the reality much later than Rosenzweig wrote about, and other guys starting from the 18th century. And you can see few devices today. We have also a European project now running on this. It's a doctoral networks project where we need to develop a thermomagnetic generator. So there's a lot of different kinds of approaches. You can really see some heavy metal stuff. But on the other hand, some people are really going to some very fine structures, and because all these people which I know, actually they're really coming from different kinds of domains. So it's really interdisciplinary research of electrical engineers, mechanical engineers, chemists, but on the other hand, solid state physics and material science, it's necessary domain, and we need to be involved together. Other applications of magnetocalorics was I was involved also in, we were dreaming about injecting nanoparticles of gadolinium into the cancer cells, not to do the hyperthermia, but by magnetocaloric effect. That was one of the projects which we did in Switzerland, and but then you have also others. You have magnetostriction and electrostriction, so materials can open or close, and that means actually that you could actually make the drug delivery as well. So there are some ideas how to do that as well. Okay, now we have a lot of challenges. The problem is that materials are not so performant as we would like to have. So this is why so huge devices. And this is on one hand. On the other hand, we have huge problems related to heat transfer. So one thing is actually the materials. Okay, there are many things, but in general, I would say these are the challenges which we need to solve in the future. And that means that we are really seeking for materials which would go beyond this, but with more modest, let's say, field sources. Cyclic stability is very problematic in some cases, also in elastocaloric materials. First order materials which are sintered are really a big problem. They can pulverize when you cycle them. You have electrostriction which breaks your very brittle PMN, PT material, for instance. So there are really different cases, or let's say needs which we need to do. And on the other hand, this is also very important. I mean, when we use the gadolinium rare earths, so I think it's an issue how to deal with this, and also how to recycle. So these issues needs to be solved, and we know that, and all the people work on this, but we are a bit too slow. So slow related to what we promised at the beginning when we started to do. Okay, we didn't know where we will come and how far can we come actually with this, but there are really challenges which demand from the community to think out of the box. And without this, the community will actually start to converge. Like it or dislike it, but that's the reality. So I think we really need to do many things, and this is by merging actually the calorics with other domains, which we see here, and these domains are related actually to thermal control devices. Why we want to do this? To get rid of all the moving parts, at least in electrocalorics and magnetocalorics, and to provide, instead of having actually a contact between the fluid and the material, the contact between materials. Then to provide actually not oscillatory flow, but actually the unidirectional flow of some fluid, which will be much more simple. I will skip the presentation of the working principle, but I will leave the presentation here so you will be able to see that or run it. How it should work actually, it's related to thermal switches and thermal diodes, embodied between the caloric materials. So this would mean actually that here in this example, this movement just presents the change of the field. But this is an example which you will see here is actually related to microfluidic thermal switch, which is based on digital microfluidics. And where we move the droplets with the, let's say, the electrostatic forces, where we change the angle of the wetting. So it's called to electrowetting effect on dielectric. So, one of my colleagues is developing this, but the major point is actually how, you know, it's really very difficult because you need to not to develop only a concept of device. You need to know people who know how to do it. That's micro engineering or even nano in some cases. You need, if you skip, let's say, this kind of devices and you want to have fully solid state, I mean, you need material scientists and you need really to strongly collaborate with them. And this is, for instance, an example how we see how from the frequency of operation, which is here today, this is the state of the art of caloric devices. We want to bridge up to here using solid state thermodiodes. And this is an enormous jump. Less than thermal diodes, I believe, or let's say quite similar, could be actually solid state thermal switches. So these two domains, from my belief, personal belief, are domains who could rescue the caloric technologies to become market competitive. Otherwise, we cannot sell so large device on the market, because I was just coming, I'm just coming from Cambridge now, where we had a conference on calorics, and one guy presented a 10 kilowatt barocaloric device, and it's a company, a startup. And okay, so I asked, how heavy is this device? And he said, few tons. And I said, okay, few tons. Do you know which is the weight of 10 kilowatt vapor compression device? No, I don't know. And I said, well, few 10 kilos. And that's the reality, you know, and this is really like two words. And I know that this startup company will get some good investors, but in reality, I don't know how far can really go, because without solving this, no go, really, no chance. We all know this. I mean, when you are really deep in the field, you know that it will not be possible. So what is possible is, I see these domains. You need to target domains where, Mikkel, just tell me if I'm too long, you know, because. So how long can we take it? 1 hour? 10 more minutes, yeah. Yeah, so look, this is the where we want to get actually, and to find the good ways, to find the gaps where the existing technologies cannot beat you, because we know that we are at the beginning. We will need next 20 years of developments to reach some levels, probably to do really something good. It's not 3-year project that you develop something from TRL2 to TRL9. I think that's impossible. So I think we should have other types of European projects where you have TRL2 to 9 in 10 years. Because some technologies are so demanding that it's almost impossible to do it in so short time. And here I just show the examples where we see the gaps which can be fulfilled. Another type of this can be seen here. So we can really clearly see that cryogenics is one domain which will be certainly very interesting, but small temperature heat recuperators which can also upgrade the heat are very interesting. High temperature heat pumps, ultra high temperature heat pumps, that means that you can really use them in industry. Low temperature thermal energy harvesters, sensorics. I mean, if you look in piezoelectrics, you have plenty of sensors already today, and then also small differential thermal energy harvesters. And which is good is also there are no fluids necessary, and perhaps you can shoot this out in the space. So which is also an advantage, and can operate at different temperature levels as well. So there is one thing which I would like to emphasize, is that we see how to bring the gap between different domains or societies where I am involved. And I'm speaking this from the experience because I'm really collaborating with many people, but also we had a lot of industrial projects. These are some of the companies here. And Mikael asked me that I give my opinion about this. How do I see actually what is really wrong? So going through over this gap, I think we can jump over. We can really try to make different kinds of let's say examples of the let's say collaboration. In general, I think it's really a big problem because I know how people think about, because I speak with them, I live with them, and in general I would say like this. Common situations. I will go through critically through all three domains. So this is the basic science where people want to see the fundamentals. We had one guy winning kind of award for titanium dioxide for solar cells, and I asked, do you already think about the company and where you could apply this? And he said, well, you know, I'm not interested for the company, I just want to know the fundamentals. You know, so that was the answer actually, and of course I would really like to build such a device, but on the other hand, I have not so good knowledge about the fundamentals, so I'm, as the engineer, I'm narrow-minded in this manner, but I can integrate. So that's my advantage, but I do not have a good knowledge on the other side. And then when we go to industry, they will not care about what we do. Actually, they will just say we need to be competitive on the market, and we just need a new product. And that's actually, when you start to think about how these people should interact, it's also probably very interesting to see where they find the financial sources. These are the main. And of course, I mean, this is market-driven. We are not so much, but we are a bit depending on them. And this is really, you know, also then how many publications people publish, because this is the aim what we are doing for. And I see also the difference. I will just give you an example in calorics. We have 1 paper of devices per 100 papers of materials. And it should be equalized better in order to have more progress in innovation. If we want to bridge this, you know, okay, for them it's quite normal that they have no publications. Some companies have, but usually they do not publish really because of the intellectual property rights and so on. Then patents, we see large number of patents are really interesting for let's say the companies. More perhaps the applied science, last in basic science, and then excellent basic knowledge. Here, excellent integrator, but actually I would say low basic knowledge, and then actually low basic knowledge and medium integrator. So it's really, you know, going from one domain to the other one. And of course, now how can we understand each other? How can we really work? That's really a question, you know, it's really a challenge. How to put these things together. I see, let's say from these two, I think that's quite simple, but we need to understand each other, and this is from one, let's say, domain where I see like how we collaborate, for instance. You know, if you know the phenomena, but you don't know how to apply it, we can find the application. I remember when we started the first electrocaloric prototype, that was the second in the world, and then we made the third one. I was with the team of electrocaloric in ferroelectric department of, let's say, electroceramics. And they said, you know, we are developing a kind of ferroelectrics which can be perhaps interesting for cooling and heating. And I said, is it electrocaloric? Yeah. And they said, but we don't know what to do now, you know. And I said, okay, let's bet that we make a machine for you. And they said, yeah, okay, let's do it. And we did even a US patent then after that. But you know, it was a collaboration where they had the knowledge how to do it, but didn't know how to apply it. And I mean, that was really interesting. But that required actually mutual collaboration. That means that my people went there and their people came to us. We need to exchange people actually to get better understanding of each other. Otherwise, it's so difficult. And this is one case which I see. So to really interact with the feedback and the mobility of researchers, the other one is actually opposite. I have an idea of device. I have no idea what can I use. So I will ask my colleagues actually, what shall I do? And they will learn as well. So it's just inverse, but actually it's the same principle. And of course, I think we need to be together at conferences. We should not just keep at basic science and not just at the applied science conferences, because we will not learn about the applications or the basic fundamental things. So you need to merge this. I know that it brings a lot of efforts, also money, but I think without this, it's really difficult actually to do it. That's really a challenge. Okay, now another one, of course, is respect each other's domains. I think that's also a very important thing. And then, okay, if we go further on, I see something because how I learned it from the applied science. I think it's very difficult sometimes to get into contact with industry. That's really a challenge. And first of all, you need to gain trust. Without gaining the trust from industry, they will say, well, look, they have no idea what they are doing. They're just dreaming about some basic stuff, and we will never apply this stuff. I mean, I know really they really think about this industry. And this is, I think, and we need to be humble. We need to, they will not be. They are very proud, yeah, and I think they will really look at us a bit from the top, you know. But we need to approach them, because without this, you can offer them measurements, master degrees, PhDs. I don't know, you can create the public competition for students to solve the given problem, but somehow you need to do this also for free at the beginning. Because if they do not trust you, that you are capable to do something, they will not do it. And this is what I see. We spent really many years to gain, let's say, the Goreni license. We have now 10 years of collaboration with them, but one or two bad events, we will lose them forever. And you know, that we do not keep at the deadline, for instance. Well, deadline, yeah, it's really, it is a deadline. It's tomorrow. You have to have it, and it has to work. So it's really a bit different way, you know. And then I think this can open the door also that you have actually PhDs and master degrees in the industry. They're your colleagues. They will understand you much better than people who are employed today. And you need that. And then of course, I think you need to invest the time to learn market needs and market applications. Sorry, I know that it's a bit strange, but we need to do that. Because otherwise we will dream about something and we cannot offer something realistic to the other guys. And then also I think the consortium with good applied science researchers can really be helpful. You lose a bit in gaining money, but together with them probably you can be stronger in finding really good partners. And you actually approach them together. That's, I believe from my point of view, really necessary to do. And by this actually, I would like to express my opinion how I think I would do it, and by this actually I would like also to finish this presentation. Thanks.
Well, thank you, Andrej, for this enlightening talk, and it's a privilege again to have a world expert in caloric technologies with us. So now the floor is open for questions.
It's not really a question, so thanks a lot for this talk. It was super interesting. I'm absolutely out of this topic, far from this topic. I really appreciate the effort you have made to give us all this information, so thank you again. I just wonder, so from the solid state point of view, at the end, for magnetocalorics, for example, at the end you have to develop a system that will work, so a magnetic system with a complex structure that will have to work ideally in, so at the end, the effort and the investment on this solid state physics, material science, will be worth it compared to what for example, what the technology that exists that you already mentioned. So I don't know. I mean, I understand that we have to move, but it will be really just comparing the effort, the weight, the crystallinity, the perfection that the system has to fulfill to be active and competitive. I don't know. As I said, I'm absolutely out of this topic. So, but I would like to know your feelings about this.
Yeah, thanks. Thank you very much. I think let's say this, people do actually research in many different temperature-related domains, and we exactly know in which domains actually caloric, magnetocaloric materials, for instance, which you mentioned, have good properties. And where we have rare earth materials, and where we could replace them. Some domains are actually fully undiscovered, let's say high temperatures, but we have ferrites there, cobalt and so on. You could mix them a bit for high temperature. Then the problem is, when I shown you these superconducting magnets, everything is actually just bought somewhere. Nobody did a custom-made superconducting magnet. But learning from superconducting magnetic energy storage systems, it's really a small amount of energy which you need to put just to sustain the magnet to be cool. Related to this, it's again, I think the answer to you would be through the application again. So I think we should not focus on all the materials. So for some domains of materials, we know that they will not perform good caloric effect. And I don't see any reason why to do such research in such domain. I agree with you. There are also problems of, let's say, synthetic materials. They will break. They cannot sustain 1 billion cycles. And they will not. So I think even if you put them in some kind of shell, that they will actually pulverize inside over some time. And I know that because colleagues from Dresden did that. And so I believe, focusing really on looking at the ranges of, let's say, market gaps, where you could come in and where you can really bring something which is competitive somehow to be used. On the other hand, to take into account also the limits of your material and not to go or pay the research in some domains for which you can already know today are worthless from this point of view. And they may be perhaps interesting for some other domains, but in general, if you retarget, let's say, magnetocaloric material for energy conversion, I think it's very clear what we are searching for, And a lot of people in domain of magnetocalorics usually show the isothermal entropy change data, which is actually so it shows you actually how much entropy change you can provide by having actually a kind of application of the field. But in general, it is not the isothermal entropy change which drives the devices. It is adiabatic temperature change, and nobody does really want to accept this somehow, to study only this part, because it's much more important. So the answer to you, yes, I think we should really be very careful which domains and which materials, and we should be very strict not to spend too much money in some domains, but rather to shift it to some others.
Thank you.
More questions? Actually, you show a wine cooler with caloric technology. I was wondering how you can compare that with also the thermoelectric wine coolers in terms of efficiency, performance.
Yeah, the wine cooler which we did was actually in general more energetically efficient than the just a moment. I will show you the thermoelectric one, but much more heavy, and it would be really expensive. So because of this, I just cannot find the mouse. Sorry. Yeah, no, I know. It's because I just need to change the presentation mode, you found it. Excellent. That's it. Yeah. So I mean, this is really heavy. I mean, this wine cooler probably had about 50 additional kilos of material to cool, to have actually, let's say, 15 watts of cooling for this kind of box. You know that Peltier, you could have only one. It would be totally sufficient to cool it down. I know that the efficiency will not be so good, but when you compare this, you know, it's a question, and then if somebody would come with life cycle analysis and request from you that you calculate the carbon footprint related to the source of the material, all from the mining up to the production, then it would be really very big problem. This is why we stopped actually research at this point in my lab. We said we will not make any prototype anymore. We want to solve first the basic issue. So some people just repeat prototypes. I don't see any reason why to do that. So coming to your question, why should we do some other prototype and spend money if it will not be better than the other one, for which we know that it will not be. And we know the reasons why. So this is why we said, no, let's stop this. Let's find out first the solution for heat transfer. And when we do that, then we can remake another one. But before that, we will not do it. And
are there more questions? Okay, well, if not, let's thank the speaker again. And Andrej will be here today in the afternoon, right? And tomorrow. So if you want to meet him in person, you are more than welcome. Okay, thank you, Andrej, again.
well, thank you.